Good evening, folks, and welcome to another episode of vBrownBag. This evening, we have got somebody that I've been talking with and very excited to share her story with because it's wonderful. We've got a data scientist, and she's going to be talking about my third love after sushi and my wife, Python. And we're going to talk about OpenCV, and we're going to talk about machine learning and all of the cool, fun new words that have been happening in the data science sphere. Leah, welcome to the show.
Yeah, great to be here.
So you and I both work at Worldwide, and we met through the course of interactions and shenanigans. And you said, "Hey, I want to be on vBrownBag," and I was like, "Oh my God, I'd love to have you on." So before we get started, I am going to go into the show notes, and that's why we've got the Worldwide logo up here. So for anybody that's curious to know about Worldwide, feel free to ask me later. If you want to, please get in on the conversation. If you are in the live studio audience, I will be fielding questions for Leah. If you are online on Twitter, you can @vBrownBag or #vBrownBag, and I'll be paying attention there, where I will be moderating and doing my best to make sure all of the questions are answered. If you want to follow Leah, she does not have a Twitter account. She is very difficult to find in the social media sphere, but you do have a LinkedIn account.
I do indeed. And as far as I am aware, by hyphenating my last name when I got married, I'm the only Leah Ellis-Clemons in existence. So I should be quite easy to find.
In existence.
In existence.
So when I was looking for a headshot for you, I did Google Leah Ellis-Clemons, and your faces. You're very difficult. Congratulations, you are very difficult to find on the internet. That's actually,
despite having such a unique name, I'm quite pleased. I thought that between the bright orange hair and the name that I'd be pretty easy to track down. But
fabulous color, by the way. I did not mention that before we hit record, but that looks fantastic on you. Good job. Okay, so again, geez, you know what? I'm a horrible host. The title of tonight's show is Flying Blind: Real-Time Video Analytics with Python and OpenCV. I'm not going to say anything more about Python or OpenCV because I am pins and needles waiting for the show to start. But let's turn the power over to you. I'm going to stop the share, and while you're getting set up, how have you been? What have you been up to since we last talked?
What have I been up to? I have not been up to too terribly much. At least in part because I've recently found that I'm pregnant with my first child, due in March, which is
oh my gosh,
exciting.
Congratulations.
Thanks. And so it's been a very busy time, but also a very unbusy time. There's a lot of planning, but not a lot of doing, an awful lot of resting.
I think that this is the very first pregnancy announcement ever on of the 3,000 episodes. I'm thinking back, and I think that this is actually the first time that we've had an actual announcement like this. So double congratulations. That's fantastic news. I'm very happy for you.
So yeah, thanks. So if you would like to think about it, you actually have two people on the podcast. So
you got a co-host.
Yeah.
a co-presenter.
Exactly. So I'll jump to it. So hi everyone, I'm Leah Ellis-Clemons. So a bit about myself. I live in the frigid land of Minneapolis, Minnesota. I'm a data scientist at WWT, as Chris said, but my path into data science hasn't exactly been a straightforward one. I joke that I started my career way down the stack as a process engineer, making hard drives and electronic device manufacturing at Seagate. And I've been slowly climbing the stack ever since. I transitioned from the process engineer role to an automation expert and kind of a liaison for the data science team while at Seagate. And after about 5 years of that, I got the courage to leap to data science full time. So I've been with WWT and the consulting services team for about a year and some change. And I've spent the last year being what I've really kind of come to think of as a total implementation nerd. A lot of data scientists are really into the model building side of things. And while that's great and while that's exciting, what I really like to do is to put all of that good stuff in action. So data science is kind of this really big umbrella that comprises, statistics, computer science, analytics, information science, the specific domain knowledge that you're working with. And I've spent the last year kind of somewhere between a conventional data scientist and like more of a machine learning engineer. But really who I am at heart is someone born and raised in the state of Kentucky. I'm a hillbilly data scientist, really. I aspire to be the data science equivalent of your redneck uncle who keeps buying these junky, broken trucks and is somehow able to get them running again using just some WD-40 and some zip ties. I'm one of those just deeply broken people that I see a nice, beefy, complex machine learning model, and I just want to see if I can get it to make quick and fast predictions on the computational equivalent of the $500 truck that you can buy off of Craigslist.
Amazing.
So with my hillbilly upbringing,
how do we get that into your title? Hillbilly machine learning special. We've got to figure out how to work this.
Truly, if that could be my brand as a person, as a data scientist, that's kind of what I'm angling for, really. It would also mean that when I open meetings with howdy and greet people with the thick accent, that, you know, suddenly everything comes into focus and makes a lot of sense.
Show up to board meetings and cut in overalls, a straw hat. Exactly.
I've gone as a hillbilly for Halloween many a time, and my friends in Minnesota are just like, "Are you sure that's not just your normal outfit?"
That's my Friday going out clothes.
Right. It's like, hey, this is my Sunday best denim. You sit down.
Amazing.
But yeah, so with my hillbilly upbringing, when I tell my friends and family that I work in data science and have been working in video analytics, they tend to react pretty similarly to this clip of Dale from beloved television show King of the Hill. May it rest in peace. While I can't get the audio to work, I've dropped a link in the chat. But what the quote is computers don't make errors. What they do on purpose. By now, your name and particulars have been fed into every laptop, desktop, mainframe, and supermarket scanner that collectively make up the global information conspiracy, otherwise known as the beast. And, you know, while I myself would love to have that sheer level of nefarious observational power, and while it's true that surveillance is a big field in computer vision and video analytics, the reality of computer vision for a good many data scientists, probably even most data scientists, looks a lot less exciting and diabolical. Your algorithm's less likely to be watching footage from a secret spy camera trying to detect people who pick their nose in public so that they can be sent straight to federal prison for life like they deserve. And it's more likely that your algorithm's going to be watching thousands of hours of falling dirt and rocks and trying to determine if the slight change in clumpiness of the dirt is indicating anything worrisome about your process. So there's a lot of use cases out there that kind of fit this niche. There are a lot of examples in the industrial space, such as monitoring images from a microscope of sensitive steps in an electronic device manufacturing process, or trying to classify the amount of product going into a piece of packaging. So if you're working in the industrial and manufacturing space, like I often am, you're probably working with machine vision, which is really just a subset of computer vision, focusing on taking the output from your machine learning model and from your computer vision model and using that to instruct other components of your system to take some sort of action, like sending something further downstream a process, downstream in your process so that it can accommodate some information that you've sent from upstream. So all you really need to get started with computer and machine vision using live footage from a camera is to basically become an amateur photographer. Super easy, right? There's an entire presentation within a presentation that I could put here on lenses, lighting, exposure time, frame rates, environmental control, but I'll spare you the amateur photography lesson and emphasize just a few things. One, if you're working with an application and a camera that you need to select the lens for, you're really going to want to put a lot of time into learning about lenses and getting this right. Because if your lens is out of focus or frames your subject incorrectly, then you're going to have a really hard time performing the analysis that you need. And that often is going to require knowing a lot about the specific dimensions of the subject you're trying to image, which leads into the second thing that I want to emphasize. Understanding your environment is going to be key to everything else. If you need to provision additional lighting, or work with changing environmental conditions, such as just shadowing from people walking through an industrial area, you're going to want to know that sooner rather than later so that you can either accommodate that through some sort of environmental control or start planning how you're going to accommodate that in your application. And the third thing that I want to emphasize is if your subject is moving quickly and you need to capture a lot of motion detail from your application, you're going to need to be operating at a higher frame rate and lower exposure time. Lowering the exposure time is going to minimize the amount of that motion blur and lower the brightness of your image. So you may need additional lighting to make up for that to image those fast moving subjects. Now, working at a higher frame rate is going to require working with a camera that can accommodate that, and also comes with a couple challenges, which will make it harder to operate in real time. So, what is real time? At its core, real time means that we are doing it live. Your application, your model predictions are all occurring with incredibly low latency as soon as the first video inputs to your algorithm are received. Many real-time applications aren't going to have an on-off switch, meaning that your algorithm will be running constantly on just a ton of footage, some of which may be totally irrelevant, and you may not want to make predictions off of or involve that footage in any retraining of your model. So to that end, you can do something called scene change detection. Think of scene change detection as kind of like in the movies. You're watching a movie and you have the protagonist and they're getting ready for a big casino heist in the hotel room in Las Vegas. And then they walk to the casino floor and sit down at the blackjack table, and another scene begins at that blackjack table. And then it cuts to yet another scene involving the expert safe cracking team in the casino vault, preparing to break in. And each of these scenes are distinct, and there's a transition point between the scenes that we as human beings can easily see and recognize. But our application can also do the same thing, and you can teach your application to detect the different types of scenes and run only your predictions or save videos for retraining during scenes that you deem as relevant. Now, how easy it's going to be to work in real time is going to depend a lot on your application and its specific needs. But we've got a few tricks up our sleeve that can make that happen. We have 4 horsemen of the video analytics apocalypse for real time, and they are edge computing, OpenCV, multi-threading or multiprocessing, and low inference compilers like TensorRT or TensorFlow Lite. So when you're working with real time, you're living on the edge, man. So edge computing, let's start with edge computing. That's when your data source and where you're performing your compute is as close as you can possibly make it to the source of data. So in the case of video analytics, your edge compute is going to be your camera, ideally. That's kind of the ideal scenario for any video analytics, is your camera also serves as your compute. And this is where smart cameras come in. These little suckers, they're cameras with a compute attached, and there's a pretty wide variety available depending on what you're looking for. There are some really highly sophisticated devices for industrial applications out there. They provide top of the line dust, vibration, and impact protection, frame rate and image clarity, while they having just a ton of CPU cores and a GPU or two on board. These are kind of like the McLarens of the smart camera world. But if you have a little bit of know-how and really just want, say, a nice and trusty, dependable 90s Toyota Corolla from the used car lot next door, it's pretty straightforward to just rig up a camera to your Raspberry Pi. I've not done that myself. It's something that I actually have in the mail as we speak, because I'd very much like to test that. But it's, from everything that I've seen online, it seems like it's a fairly straightforward process if you want to DIY yourself a smart camera. So there's
I wish you would have told me that you needed a Raspberry Pi. I could have sent you one.
Yeah, this is actually my first time working with a Raspberry Pi.
Is it really? They're so much fun.
I'm super stoked. The last time I tried to work with a Raspberry Pi, I ended up leaving Kentucky and moving to Minnesota, and that kind of fell to the wayside of moving 12 hours north.
A couple of questions from the audience, and I forgot to ask you this at the beginning. Would you prefer us to table all questions to the end, or would you prefer a more organic back and forth Q&A as we go through the slides?
Totally fine with an organic back and forth Q&A.
Okay. So the first question was, so if the McLaren is if the McLaren smart camera is the multi GPU, multi-threaded super camera with vibrational stuff,
Yeah.
and the Toyota is the Raspberry Pi, where does the deep lens fall in between in that description?
The deep lens. I can't say that I'm too familiar with the deep lens.
The AWS deep lens, it's it's their hold on, I don't want to screw it up, but AWS sells a product called the Deep Lens. It's first learning enabled video camera for developers.
I have not heard this.
If you're not familiar with it, then never mind. I was under the impression that it was maybe a couple of Raspberry Pis cobbled. It's, you know what? I think I just found your next purchase for you.
Yeah, I'm looking at this and I'm like, oh boy.
Okay, then disregard if you're not familiar with it. They are $250 on Amazon.com.
Yeah, I would guess that they are somewhere near the more accessible models of it, since a lot of the ones that I've been working with, specifically the one like really beefy ones for your industrial applications, those typically run on the order of a few grand a pop.
I imagine the things that you work with are like the creme de la creme, the things that they're putting up in factories for all kinds of crazy detection stuff. So we're curious about your opinion of the deep lens, but if you've never heard about it, please disregard.
Yeah, no, I'll definitely look it up though. Thank you for whoever pointed me in that direction.
The other question was around scene changes and the level of difficulty, and the question was, is that why computer vision in cars is difficult, because the scene is always changing?
Yeah.
The lighting is changing and the scene is changing. All the things are like constantly in flux.
Yeah, having not worked with any of your like car navigation and kind of car focused machine vision and computer vision applications, that would definitely be my guess. Is there's a wide variety of scene changes. I'd guess that there's a ton of work done in kind of more edge and border detection for finding the roads, detecting cars in front of you and things of that nature. Gotcha. I'd also guess that these are trained on just a ton of footage.
Yeah, 100%.
So yeah,
cool.
No, I find the world of your smart car, like your smart navigation, so fascinating, but so much of it is just kind of locked away in the secret vaults of the various auto manufacturers.
You got to keep that secret sauce.
I know. I grew up, my dad worked for Ford, and so much of my family's worked in automation. And so that's the first thing that they always ask me about is, oh, do you make the cars go? And I'm like, it sounds like it would be cool, but so much of that's just kind of the secret sauce right now.
Gotcha. Okay, cool. Thank you. No more questions right now.
Yeah. So just going back to edge computing, there's a number of benefits to computing on the edge. Namely, that you get some exceptional response times and you don't take up half as much bandwidth as you would otherwise, because you don't have to worry about the time or the data that it's going to take to just transfer video from the camera to another server and then take whatever that decision, whatever predictions or whatever output that gives, and then send that to somewhere else in the system if it's going on to impact other decisions. So really, you have so much less lag. And which really makes a difference in your high FPS, high frame rate applications, because that's so much more data. If you go from, 5 frames a second to 40 frames a second, suddenly you're working with so much more data and so much more lag. And so for any high FPS or high resolution, high detail, or high memory inputs, edge computing confers huge benefits. And I really cannot overstate how beneficial it can be to get things to run on the edge, and why it's often worth throwing the extra money at getting a nice beefy smart camera to work with on the edge. So regardless of whether you're working with the McLaren or the used Toyota Corolla of the smart camera world, as long as you've got more than 2 CPUs, you can utilize multiprocessing to get even more benefits to speed. If you think of your application as like a restaurant, multiprocessing is like having a few chefs in your kitchen versus having one chef do it all themselves. Each chef has their own station, and you can hand off individual tasks to each chef for them to focus on exclusively. Multi-threading is pretty similar, but instead of individual stations for each chef, you have each chef working on their own set of tasks, but often utilizing the same kitchen space. So in video analytics, this means a few things. Instead of waiting for each incoming video batch to go through all the steps before you're able to start grabbing and computing the next video batch, you can go and start having all the threads ready to handle these individual tasks. You can have one thread focused on grabbing and transforming the incoming data. That thread can pass the data to another thread focused on making predictions using a convolutional neural network, and then passing that video to another thread to save that video to a cloud storage. And all of these can work simultaneously so that you don't have to have this kind of gap while you're waiting for everything to finish before you can look at the next batch of footage. Which is really, as you can imagine, intensely important when you're trying to work in real time to not have those gaps. So there is a limit, which is that the max number of processes you can really run without running into lag or memory issues is the number of CPUs of your device minus one. You've got to keep that one CPU free to run your operating system, background processes, and things of that nature. So I'm only going to spend a bit of time on this next one because it's kind of its own can of worms. But if you're working with some complex deep learning models, or a particularly deep convolutional neural network or variational autoencoder, or generative adversarial networks, you can sometimes run into algorithms that take longer to predict than your latency requirements will allow for real time. This is where TensorRT and TensorFlow Lite come in. These are two really popular inference compilers for TensorFlow that have a number of differences in how they operate and how they achieve this. But at their core, they are just these lightweight compressed versions of TensorFlow models that optimize your model, optimize their memory footprint while really maintaining its integrity. I like to think of it as, think of your model as a car. This is like attaching rocket boosters to the car. I've taken a variational autoencoder that would regularly take about 5 seconds to make a prediction and got it to about a half second by just converting the model from a TensorFlow model to a TensorRT model. So these things are super powerful. TensorFlow Lite is a bit limited, and you'll see it often on Android and Windows, I believe. They don't have anything for Linux, and I've mostly been working with Linux devices in the past, so I don't have quite as much experience with TensorFlow Lite, but TensorRT can work on a variety of operating systems, and TensorRT really, just as long as you have a GPU, TensorRT can go. So highly recommend using those if you're working with any complex models and you're looking at your lag going, oh God, this is not going to fly. So we've now met our first three horsemen of the apocalypse: edge computing, multi-threading and multiprocessing, and lightweight inference compilers. So those are our war, famine, pestilence. And now we can go on to our fourth horseman, the leader, death itself, which, as far as I'm concerned, is OpenCV, or the open source computer vision library. So my husband is a software developer, and he's only recently had his career go in a direction where he's had to work in Python at all. He's kind of been a .NET guy for the last decade or so. And so he started working with Python, and he started learning about PEP 8 standards and the Pythonic way of coding. And he comes to me and he's like, Leah, I know that you like Python. I know that you work in Python, but I'm pretty convinced it's a cult. And so if he is indeed right, and Python is a cult, then video analytics is a sect within that cult, and OpenCV is our cult leader. OpenCV, as far as I'm concerned, knowing nothing about C and C++, which is what it's all built on, it's pure magic as far as I'm concerned. It's written in C, C++, interacted with using Python wrappers, so it can perform these computationally intensive tasks at just absolute breakneck speeds and in a way that's so easy and intuitive for Python users such as myself, who, per my husband, aren't real developers. So I know he's very mean.
And opinionated.
He is, but it works out well because I'm also mean and opinionated. So we work well together.
As long as it balances out.
Oh yeah. But yeah, so OpenCV, it's got its tendrils in almost anything you could ever want to do in video analytics. And really it is perfectly optimized and in fact designed to work in that real-time space. It can read and write videos and images. It can transform images by resizing them. It can convert images to grayscale or other color schema. You can blur images, draw stuff on images, concatenate images, perform edge detection. And all of this is only the tip of the iceberg when it comes to OpenCV. There is really just so much that you can do with OpenCV that if you are unsure if something can be done in real time, or you're doing something another way and you're like, man, I really wonder if I can make this faster, this video transformation faster, look at OpenCV. There's just so much that's been developed for OpenCV that it's definitely worth taking a look. So I've worked up a quick demo of what our four horsemen look like in action. So I'm using a slightly modified version of a model developed by Data Lyra on Kaggle. This model can take images of Lego bricks and classify the type of brick with just under a 70% accuracy. I've taken this model and productionalized it to use a simulation of real-time video input that should run on most laptop environments. So I have all of this code, as well as a link to the exploration and work that Data Lyra did that went into the original Lego classification model. Have that up on GitHub, and I will get a link out after this. And you can take a look, deeper look into the project if you want. So to keep things simple and easy for folks new to video analytics and real-time computer vision, I'm not using any of the lightweight inference models that we talked about. So we're not using TensorRT or TensorFlow Lite. And I'm also not using an edge device for this project. Our edge device in this case is simply our laptops. So we're not working with real, true live video here. So you don't need to worry about having to have a camera on hand. This should run just fine on a laptop. You don't need to worry about having a GPU or any of that good stuff. We're working with some fairly lightweight stuff as far as real-time video analytics goes. So to start, let's talk about the core structure and how this utilizes multiprocessing. This application has a main.py script that starts the whole program execution. And from there, it spawns its first thread, capture vid.py. This thread simulates the grabbing of images from a live camera device and sticks those into batches of 20 frames in a multiprocessing queue. When I originally got this on Kaggle, these images were all part of a just single repository of all of these Lego images. I split that into a train and a test set, and then a validation set, which is what I then used to actually create a little video. So I did that by taking the individual Lego images, saying, okay, we're going to put 20 frames of this into a video, and then including some random blank space between each of those Lego images. And so I will show that video really quickly, and let me pull up that file. So that we can really get an idea of what we are working with here.
Is that Jupyter in VS Code?
Yes, this right here is.
Nice.
You know, I spent years hating on VS Code for no reason, and then started working with it extensively, and I'm a convert. What can I say?
It the IDE discussion is one that always turns into something quasi-religious. So I don't care. I just use whatever is available.
I have seen more intense fights about IDE preferences than I ever have at sporting events, which is impressive. I'm going to, it looks like I have to share another screen of mine to get this to work. So
okay,
give me one moment. And I'll see if I can get things to cooperate for me. That is one thing that I wish I could just share videos from within VS Code. That's one thing that I've not yet found how to do.
We'll work on that for the next presentation, and and piping audio through your Zoom setup.
I'm very high maintenance as a presenter, so.
You're still not as bad as Ben Kehoe, and Ben Kehoe is going to hear this and see this and be like, "Hey, wait a minute."
All right, are you able to? Oh gosh.
Yes. Oh no.
One moment.
Sure. This is what happens when the demo gods have not been appeased ahead of time. This is actually technically my fault, because I did not sacrifice the appropriate number of chocolate bars to the demo gods. Yeah, Graham called it. It's because it's live. That's why.
Yeah, well, as a currently pregnant person, I can attest that I've sacrificed the appropriate number of chocolate bars. So I've got it covered. Okay. It will not let me. Are you able to see the video?
Yep, I see the video.
Okay, so that is a sample of what our input video is going to look like. So while the algorithm and the individual predictions are going to be made on individual frames of this video, what we're actually going to be making the predictions on is this as a simulation of real time. This is operating at 20 frames per second, and that will be the input that we're working with. And maybe when I try to show the other video as part of this presentation, it will go a little bit more smoothly. But we will see if I am able to be so lucky.
So for your, oh, it's coming up.
All right, are you able to see?
I see the presentation.
Jupyter Notebook.
Yes, see your Jupyter Notebook.
Beautiful. So, actually, let me get this video to stop running. So that is the input video that we are working with. Okay. And if we go back to our presentation for a brief, oh, why? Sorry, we're clicking all the way through it again. I've always said that if I was going to start a podcast, a tech podcast, it would be Leah Ellis-Clemons' Technical Difficulties podcast.
That would be, I would watch that. I would use a bingo card to figure out which ones I've accomplished as well.
It would be part comedy, part technical talk, all tragedy. So we have our main PY script, and what that does is that uses a multiprocessing queue to pass an empty video queue over to this capture vid, which starts grabbing images and putting them into batches. So the big thing about multiprocessing queues is that is our way for the individual threads to communicate, because these threads, they are totally isolated from each other unless you specifically go to talk to them, talk from thread to thread using these queues. They are going to continue to do their own thing in their own little world. So we start up the first thread and we pass to it an empty video queue. And what that thread does is it starts just pouring video in and batches into these queues. So it grabs images and puts them into these 20 frame batches, and then starts handing those to two other threads. One, which is making predictions on Lego brick types. So that's using the model that we just talked about. And the other is actually performing a nice little edge detection algorithm where it's going to pop up an image with all the edges highlighted, and it will save those images to a new video file. So those are kind of the three threads at play here. And again, they're all able to operate simultaneously. We don't have to wait for the batch camera to grab a batch of 20 frames and hand it to make the prediction. And then the prediction hands it to the edge detection, which performs that and saves the video. And then we get to grab another batch. We're just grabbing batches, and it's just constant moving. Constant moving action. So we are able to operate in real time. The only difference that this makes, if we were to be using real time instead of this real-time simulation, so if you were to hook this up to an actual camera, is that you would be performing your operations a little bit differently to connect with the camera, depending on the specific needs of your device. But in terms of that, you're going to be grabbing video, putting them into batches, sending those batches out to have your algorithm and whatever else you're doing work its stuff. That core is all the same. So back to the Visual Studio here. We can talk a little bit about OpenCV because while this application is pretty lightweight, part of the reason why it's so lightweight is because of the magic powers of our cult leader, OpenCV, and its mysterious ways. This is a little bit on how that edge detection work actually is being performed and what that really looks like. So if we import CV2, which is OpenCV, and import some plots so that we can matplotlib so that we can view some of the images here that we're producing. And then I will be grabbing from this dataset folder, that is the individual images that we started working with. So I'm just taking this random one of a brick corner, and we're going to be performing all of the little operations that we will be doing on this live video. And suddenly my computer seems to have crawled to a stop.
Not the way of it. There we go.
Okay, we're back in business. So this is our first instance of what we're using CV2 for, OpenCV, is we're just reading in an image. It's just a quick, easy, simple reading in an image. And then this is what that image looks like. It's just a nice blank background and this fun little corner Lego brick, which I always found to be the most painful to step on. And from there, we're going to be looking at this find edges function. So I'm going to go into our source code and we are going to look at this save edges script. So what this find edges function does is we first convert our image to grayscale. Since really what a lot of your edge detection algorithms like is they're looking more at pixel intensity. They're not really looking so much for color shift as they are focused on intensity shift. And so by converting to grayscale, you're just looking at pixel intensity. You're getting a really good snapshot into that specific component. So first we begin with converting to grayscale. Then we're going to be performing a nice Gaussian blur, just quick and easy to eliminate some of the noise that can really improve some of your edge detection algorithms. And then we are performing this nice canny edge detection right here. And again, all of this being done in OpenCV, and OpenCV again, this canny edge detection, it takes maybe a matter of a split second for it to do. And a lot of OpenCV, a lot of your OpenCV functions and things like this, it's all packaged. There's quite a bit that goes into canny edge detection itself, and OpenCV packages all of that nicely for you in one easy to use function. And then we are going to convert it back from grayscale to BGR color format so that everything else will play very nicely when we go to save the video later on down in Save Edges vid. But we'll get back to that. So let's find our notebook again. So to start, I'm just going to break these down into the individual components of what that looks like. And again, most of this 1.6 seconds is generating the plot, not OpenCV working its magic. So we start with this image. By converting to grayscale, we get a little bit less of that nice warm gray character. And then by performing a blur, and this blur makes only the slightest bit of difference. It's really just reducing that noise. You can see that a little bit around the edges and around these little knobs here. And then this is the fun part. This is the canny edge detection, where we can see exactly where some of those edges are. And by varying the different parameters that you're using for these blurs and these edge detection, depending on what you're hoping to get out of it, how many, like what detail of edges are you really looking for? Do you want just the most fundamental outline of whatever your subject is, or do you want some of that finer detail? You can vary some of the parameters here. I've opted to go pretty bare bones and just focusing on kind of the gross outline of everything. And just one thing to note, why would you want to ever do edge detection? One thing that I've been actually very interested in lately is how you can train models entirely on just looking at edges. So you can go and take your subject and take a video or an image and get just the edges and feed that into a model. And then you would be making predictions on input that's, again, after this edge detection has been performed. And I think that's very interesting. And that's part of what led me down this path to begin with. So yeah, a lot of the magic in this and all of the transformations that are performed is through OpenCV. Let's take a peek at what our camera stuff looks like, in that these video capture and video reading components, that's all done in OpenCV. We do a little bit of resizing of the image so that we can feed it into our model here in the prediction. So really, again, I cannot stress this, OpenCV has its tendrils all over video analytics. And if you're working in real time, I would be very surprised if you're doing real-time video analytics in Python and you're not working with OpenCV. It is, as far as I'm concerned, real-time video analytics in Python begins and ends with OpenCV for a good many folks.
And there's some really good tutorials for OpenCV as well. Some if people are wanting to get started with it, there's a lot of good literature out there, even in the OpenCV documentation itself, on like how to start kicking the tires on it.
Oh yeah, OpenCV documentation is incredibly detailed. It is awesome stuff, and there's and I'd be happy to provide these links as well. There's a fantastic course on Udemy, and then one that I want to say I found through LinkedIn Learning that are just top notch. When I started working with OpenCV, that gave me kind of the full toolkit that I needed to get started.
Yeah, if you could provide those, I'll tack them into the show notes for afterwards. That'd be wonderful. Thank you.
Yeah. So let's see this in action. So we have our main.py. This is going to go and spin up our threads. And when we get this started, what we're going to have is we're going to have a log that is generated where some of our predictions and just kind of some of our error keeping will all be stored. But you will be able to see those predictions in line. Now, again, accuracy of these predictions is less what I'm trying to highlight here, because you will see that quite clearly our algorithm could use some work. But this should give you a good idea of what this looks like in production. So moment of truth, we've hit run. And it's going to take a bit for our TensorFlow model to get started. One thing that, since this application, this moves so quickly that we don't really have to worry too much about it. But if you are, if your predictions take a bit of time, or your algorithm takes a bit of time to start working and load in your models, then you may want to kind of initialize all of this ahead of time before you start making your predictions. Build in some sort of delay between your first batch when everything starts getting loaded in, kind of build in like a dummy batch, and then wait for everything to finish loading before you go and kick into the big real-time predictions. So there's our model loaded in and all of its details printed here. And we've started making predictions. We've got our blank image. And there we go. So we're starting to catch up now. Blank image, flat tile, round 2x2, brick 2x3. And let's give this a bit so that we can save a video in this edge detect video folder. And then I can show you what that output looks like. But yeah, so now we are making predictions in real time.
Based on that first video,
Yes.
Okay, cool.
Yep, based on that first video there. That is our input. So speaking of scene detection, let's go and take a quick look at Lego Predict, because remember, we only want to predict. We don't want to predict on those blank frames, right? Because it's going to look and it's going to be like, oh, there's no Lego brick here. And if it tries to guess, it's going to guess something wildly wrong. So one thing, and again, this is arguably scene detection in its very most fundamental form, because this is really nothing even remotely fancy. I'm going to go in and stop this running real quick. And what this really is just checking to see, do we have any pixels that are all of our pixels black? Do we have a totally blank image, or do we have something there? And only when there is something there do we go on, add this to this item list array, and go in and perform our predictions. So if we have anything in that batch, we're going to start making those predictions there.
Gotcha.
So now I will try and play another video to show off the edge detection and what that looks like.
10,000 changes in Git. That just gives me a ulcer.
Oh, where was that? Was that in Visual Studio?
Yeah, I was looking at your Git notifications of number of changes, and it was like 10K. I didn't even know you could get up to 10K.
I didn't either. It is not quite as bad as my email inbox, I will say.
Amazing.
I am. I would say that I'm highly organized, but not in the most conventional sense.
Graham says push often.
Oh yeah.
Remember that old there's two kinds of people in this world, and one person's got the iPhone with like 10,000 unread messages on there, and the other person has like all of their notifications like checked off, and it was like a clean slate. I'm the latter. I'm definitely not the former.
Oh yeah. I have so many notifications. You sign up for some email from some website once and then never read it again, but still get them, never unregistered. Okay, so I have the screen sharing now, and we can actually look at the video here. So this is what our edge detection video looks like.
Nice.
It's taking that exact same video that we were looking at before, but it's found the edges and it's output those to its fully separate video. And it's doing all of this while the predictions are working their magic and telling us what it thinks it is.
Oh, I like the one with the angry eyes on it.
Oh yeah, I relate to it a lot. But
awesome.
Yeah. So that was all I really had for the demo. Just to really highlight those two components on that I think are highly accessible and that anybody can run on just standard laptop to get an idea of what multiprocessing looks like in practice for video analytics, and just a teaser for OpenCV's magical capabilities.
Clearly, you are an acolyte of the cult that is OpenCV.
Oh, absolutely. I've been joking with a friend of mine. My husband is a death metal musician, and I very much enjoy that type of music as well. And I play the drums, and I've been jamming with a friend of mine, and I've told him since he's recently started learning Python, I'm like, do you want to just write music about OpenCV? And he's like, Leah, this is the weirdest idea you've come to me with. So
really? That's the weirdest idea?
That's what my reaction was. I'm like, I'm pretty sure I've thrown some more odd ones at you. But
I've got way worse that in the back of the old melon.
Right. I'm like, I thought we'd talked about something weirder than that in the last 5 minutes, I'm sure.
You know me, man.
Yeah.
Okay. This was amazing. The repository. Could you put the repository link in the chat channel for the people in the audience, and then I will also post it in the show notes.
Yes, indeed. Part of why I am normally I'm normally big into the push often, but unfortunately, when I'm left to my own devices, working alone to get something together, using Git gets thrown out the window, and so I'll be pushing that to a repo immediately after this, and then I will be sending that link along.
Wonderful, appreciate it, and I'll put it in the show notes Graham, Rob, Olukunle, and everybody else that's watching right now. I will have that in there in the YouTube show notes. So we will post that within a day or two. This was amazing. And also let's get the links from you for the Udemy courses, so that if anybody wants to get their feet wet with OpenCV in a tutorial based scenario, then we could get them on that path as well.
Yes, indeed. So I will pass along the Udemy courses and those learning resource recommendations, and then I'll have the Git repo both for the work that I've done on productionalizing this, but also the original model that I took a lot of inspiration from.
Am I saying that wrong? You said Udemy, and I say Udemy, but I've never heard anybody say it out loud. So I don't. Am I doing it wrong?
I don't know. I know that generally speaking, from my hillbilly raisin, I just assume that I pronounce things wrong, because I still will occasionally say, I wash my clothes in a wash.
I say sandwiches and wash and all that stuff.
Yeah, I told someone once, oh yes, I'm going on a trip to Washington, D.C. shortly after I moved to Minnesota, and they were like, you are country.
How do you pronounce Udemy? How to pronounce it correctly? Oh, from the Udemy website, no less. All right, hold on. Here, I'm gonna hit play. Oh, actually, you know what? I don't care. Everybody else can Google that. I don't care. You said it right. Udemy.
For once.
All right, Leah, this was amazing. This was everything I hoped it would be and more.
Yeah, that is so good for me to hear. That is wonderful. I've had a great time.
Let me make sure that nobody else has any questions on the website. Let me, you know what? I stink. I didn't even go into TweetDeck. Let me make sure that nobody has, nope, I think we're clear. There are some folks saying thank you for this and great show, but no additional questions. So brilliant, amazing, wonderful. Great. Yeah, feel free to reach out on LinkedIn or wherever you apparently can find me on the internet, as I'm apparently quite elusive. You are. You're very elusive. You're wily. Folks, thanks very much for attending another episode of vBrownBag. We will be back next week with another great chat. So thanks and have a great night. Leah, thank you once again.
Thanks, Chris.